Well, good morning, good afternoon, everyone. Welcome to the new event of the ESO Hypatia Colloquium 2022. My name is Giacomo Beccari. I'm very happy to welcome you to the new seminar. Of course, I would like to congratulate immediately with the two speakers of today. They will be introduced in a minute by the chair of today, who are Melanie and Ivana, who are fellows and a student here at ESO Hypatia. So thank you very much to them also for contributing and helping in making the event possible. Just for my point, the usual technical aspects. First of all, to the people that are connected via Zoom, please be aware that this event is live streamed on YouTube, and hence, if you are uncomfortable with that, please, I ask you to please leave the meeting. Then you can still join, of course, and attend the talk on YouTube, where you can also make questions using the live chat. Same, if you can, you will be asked and you will be allowed to make questions at the end of each talk by using the internal chat, or you can also raise your hand if you are on Zoom, and then you will be given the possibility to make the question yourself. Please, if it is fine with you, and it would be nice if you can also introduce yourself to the speakers. As finally, you can also send questions anonymously using a web form that is available online on the Hypatia web pages. With that, just let me remind you that the talks are available on YouTube, where they will stay on a dedicated playlist, and the videos are also linked from our program pages, where you can also, if you click on the title of the talks, you can also have a look at the curriculums of our excellent early career scientists who are making these events possible. With this, I will close here, and I will leave Mary now the floor to start the event. Thank you very much, and see you later.
I will just have to figure out how to actually show my screen.
Yeah.
And also allow for the first speaker to start sharing. Okay, well, it's my pleasure to introduce the first speaker of today's session, Dr. Stefania Barsanti. So Stefania is a postdoctoral research fellow at the Australian National University in Canberra. So she's actually currently joining us from Canberra, where it's 1 a.m. So thank you very much. So Stefania broadly is interested in galaxy evolution. She researches stellar populations, galaxy angular momentum, galaxy environment, and the cosmic web, and links all of these. And today she'll be discussing with us the observed link between spin filament alignment flips and bulge formation. So Stefania, go ahead and share your screen, please.
Okay, so. Okay, can you see my screen?
Yes, and we can hear you clearly, so feel free to go ahead.
Thank you. So hi, I'm Stefania, and today we'll speak about an observed link between spin filament flips and bulge formation. So the key question that we try to address is how do galaxies build up their angular momentum, and in particular, how the spinning of the galaxies within the cosmic web is related to their galaxy properties. So from simulations, looking at how dark matter halos spin in the cosmic web, we see that they have a preferred alignment with respect to the closest filament, and this alignment is mass dependent. So we see that the high mass halos tend to have a more perpendicular alignment with respect to the closest filament, while low mass halos has a preferential parallel trend. And this signal is also redshift dependent. So we see for the low redshift region a stronger perpendicular alignment. Regarding galaxies, both the simulation and observational studies have found that also galaxies show different spin filament alignments, in particular according to the morphology and stellar mass. And I would like to particularly highlight the result of Welker et al. 2020, where it has been confirmed in the observation that there is this stellar mass dependency of the alignment of the spin of the galaxy with respect to the filament. And so if we have on the right, so we have a schematic representation. So for a late type low mass galaxies, the spin of the galaxies is in parallel with respect to the direction of the filament within its embedded. Instead, for more elliptic and high mass galaxies, the direction of the spin is perpendicular with respect to the filament. And these alignments gives us important insights about the formation pathways of the galaxies. In fact, the parallel alignment is a sign that the galaxy has been formed through gas accretion. Instead, the perpendicular alignments are a sign of mergers. So if we have a merger happening along the direction of the filament, this will cause the flip of the alignment from parallel to perpendicular. In this work, what we want to do is to explore the spin filament alignments according to various galaxy properties. And we focus on stellar mass, morphology, galaxy kinematic proxies, and also the bulge and disk components. And what we want to do is to understand the physical tracers of the alignments and to find the primary parameter of correlation. We also want to study the separate bulge and disk spin filament alignments in the observations. And to do so, we take advantage of the gamma survey to reconstruct the cosmic web, and of the SAMI survey, which is an integral field spectroscopic survey to measure the galaxy properties. And this will give us insights about the formation of galaxies, bulge and disks. So the gamma survey is a spectroscopic and photometric survey up to redshift 0.5, but we are going to focus only on the low region up to 0.1 because that's where we have the overlap with the SAMI survey. And so we use gamma galaxies up to redshift 0.1 to reconstruct the cosmic filaments. So these are the free gamma regions. And so to reconstruct the cosmic web, first we reconstruct the density field using a three-dimensional Delaunay tessellation, and then we use the filament extractor disperse, which has been used already a lot in the simulations and also other galaxy surveys such as GAMA and SDSS. So disperse it's really powerful because it doesn't make any assumption about the distribution of the galaxies, and we can reconstruct the typical cosmic features such as the voids, walls, and the filaments, and we can also apply a signal-to-noise threshold in order to keep only the most robust features. So these are the three gamma regions, and using the 3D coordinates of the galaxies, so the right ascension, declination, spectroscopic redshift, we can actually reconstruct the density field in 3D. This is a representation using the Delaunay tessellation field estimator. So in 2D, in the Delaunay tessellation, we will have triangles. In 3D, we have this typical tetrahedra that show the density field. Now we use the density field as input to disperse, and for the free gamma region, we can actually reconstruct the cosmic filament. So this is again a reconstruction of the in 3D of the gamma cosmic filaments. So to measure the galaxy property, instead, we take advantage of the integral field spectroscopic SAMI survey. So we select around 1,000 SAMI galaxies with a cut in stellar mass starting from 10 to the 9 solar masses, having an ellipticity and a kinematic position angle. So the kinematic position angle is measured from the velocity map of the galaxy. So this is a stellar velocity map, an example for a SAMI galaxy, where the black line represents the axis of rotation and the green line represents the estimated kinematic position angle. And then we want to study the alignment as a function of the bulge to total flux ratio, which is basically a proxy for the galaxy morphology. And this bulge total to flux ratio has been measured through a two-dimensional photometric bulge disk decomposition. So given on the left the image, the photometric image of the galaxy, we fit an exponential disk component and a Sersic bulge component in order to reconstruct the image of the galaxy and to estimate the bulge to total flux ratio. And finally, we define the mass of the bulge as the geometric product between the stellar mass and the bulge to total flux ratio. So we also take advantage of the 2D kinematic bulge disk decomposition. So here we have the 3 rows that represent 3 different galaxies, and the first column represents the stellar kinematic map for the galaxies, similar to the one that I showed before. So using this 2D kinematic bulge disk decomposition, which is based on the photometric bulge disk decomposition, we can actually decompose the velocity map of the galaxy into the bulge and disk component. So for some galaxies, the disk component will be the dominant one, or the galaxies will only have a bulge component, and then cirrus galaxies will be characterized by both a bulge and a disk component. And in this way, we can estimate the separate position angle for both the bulge and the disk. Now, looking the gamma region in 2D, this is a cone plot with right ascension and redshift. So the gray points represent the gamma galaxies that we use to reconstruct the filaments, which are shown in black. So these are the projected the lines are the projected filaments. And then the red points are the SAMI galaxies. So the galaxies for which we want to understand the alignment of the spin vector with respect to the closest filament. So the first thing that we do is to assign to each SAMI galaxy the closest filament. So this is a schematic representation where we have the galaxy, we have the vector representing the spin, and this is a filament, representation of the filament with the orientation vector of the filament given by this person. And we can estimate just with the Euclidean distance between the galaxy and the filament, and the distance between the galaxy and the node, which are the high density field regions. And to parameterize the alignment between the galaxy spin and the filament orientation, we just use the 3D angle between these two vectors. So here we have the cosine of the angle between the vectors, which means that a cosine value towards 0 means that the angle is 90, so we have a more perpendicular alignment. Instead, value equal 1 means a more parallel alignment. So to measure the 3D spin, we use the thin disk approximation, and in spherical coordinates, the spherical coordinates of this vector depends on the PA, which is the position, the kinematic position angle that's estimated from the SAMI velocity map, and also the inclination angle, which depends on the ellipticity and the intrinsic flatness parameter, which is morphology dependent. And then we just transform this into the equatorial Cartesian coordinates. So that as I shown before in the schematic representation. So how do SAMI galaxies look like in the cosmic web? If we plot the bulge to total flux ratio as a function to the distance to the filament on the left and the distance to the nodes to the right, we can see that galaxies that have high bulge to total values, so more bulge dominated galaxies, are closer to the spine of the filament and to the nodes, while more disk dominated galaxies are farther away. And this is consistent with the morphology density relation of Dressler, where we see that elliptical, for the galaxy environment, where we see that elliptical and S0 galaxies mainly dominate regions of high galaxy density, while low galaxy density regions are mainly populated by spirals and irregulars. So if we plot the alignment angle as a function of stellar mass, bulge to total, and bulge mass, we can see that there are variations in the median of the alignment angle from more parallel towards more perpendicular values, starting going towards higher values of these properties. So we see that galaxies with a higher value of bulge, a lower value of bulge mass, have a more parallel alignment, while galaxies with high bulge mass has a more perpendicular alignment. And if you apply a Spearmart test, we can find a correlation between these galaxy properties and the alignment angle, which is particularly significant for the bulge formation. So we found p-values that are lower than 0.05. Now, in order to understand which is the primary parameter of correlation, apart from these three galaxy properties, we also study other galaxy properties that the simulations show to correlate with the spin filament alignments, such as the stellar age, the degree of rotation within the galaxy, the distance of the galaxies to the filament spine, the kinematic misalignment between the gas and the stellar component, and the local galaxy density. And if we apply a partial list square regression technique, which aim to discard redundant parameters, we can find the parameter that show the strongest correlation. And in this case, we find that 70% of the variance in cos gamma is actually explained by the bulge mass. So we find that the bulge mass is actually the primary parameter of correlation. So it's the primary parameter according to which we can predict spin filament alignments for the galaxy. So if you look in more details, the trend of the alignments as a function of these properties, we can plot the probability distribution function for the cos gamma, where the values go from 0 to 1, so from a more perpendicular alignment to a more parallel alignment. And the galaxies are binary according to ranges in stellar mass, ranges in bulge to total flux ratio, and ranges according to the bulge mass. And we see that for high values of stellar mass or high values of bulge to total, so basically the red and yellow lines, and high values of the bulge mass, we see a more perpendicular alignment. Instead, for low values of stellar mass, so the blue line, or low values of bulge to total and low values of the mass of the bulge, we see a more parallel alignment for the galaxies. And to assess the statistical significance of this trend, of these trends, we compare them with a uniform distribution, which is marked by the PDF equal 1 by this black dotted line. And we see that according to the Kolmogorov-Smirnov test, we actually find that the trends have p-values lower than 0.05, and they are statistically different with respect to a uniform distribution. Now we also look at other properties, and if we select galaxies in visual morphology, such as late-type galaxies, or in star formation activities, such as star-forming galaxies, or in degree of rotation, so fast rotator, or in a galaxy environment, such as isolated galaxies, we see that if we select all these classification of galaxies and we choose the ones that have low bulge mass, we see that they have a more parallel trend. Instead, if we choose those ones that have a high bulge mass, we see a more perpendicular trend. And we can see that these other galaxy properties can just be considered as secondary tracers of the spin filament alignments, and they correlate with the alignments just because they correlate with the bulge of the mass. And so looking now in more details at S0 galaxies, we decide to select S0 galaxy according to visual morphology, also select only fast rotators and galaxies that are well fitted by a photometric double component profile, so an exponential disk and a Sersic bulge. So for us here we have the probability distribution function for S0 galaxies, and in green we have the trend for all the galaxies. We show a higher probability distribution function for the perpendicular trend. And splitting this sample in stellar mass, we see that the galaxies in high stellar mass, so the most massive S0 galaxies, actually dominate the perpendicular signal. Instead, the PDF is higher for low stellar mass galaxies for a parallel alignment, which is not actually statistically significant, so it's consistent with a uniform trend for low stellar mass galaxies. And if we look at the bulge Sersic index distributions of S0 galaxy, again splitted according to stellar mass, we see that the two galaxy populations are statistically different according to the KS test. And in particular, we see that most massive S0 galaxies tend to have a bulge Sersic index equal 4, so the classical devacular profile. And this signs tell us that so the main formation pathway for these galaxies are mergers. Instead, if we look at low stellar mass galaxies that have lower, also have that have a parallel tendency towards a parallel trend and lower values of bulge Sersic index, we see the mergers cannot be the dominant mechanism, so maybe gas accretion or faded spirals could be a possible mechanism. So looking now at the separate bulge disk spin filament alignments, so we
2 more minutes.
Okay, thank you. We see that, so we have reliable kinematic measurements for around 468 bulges. And if we look at the morphology histogram, so in red we have the bulges, which are mainly early type galaxies. Instead, the disks mainly trace late type galaxies. And then we have around 200 galaxies that have reliable kinematics for both the bulge and disk component. So if we look at the separate alignments for bulge and disks, on the right, so here again we have the PDF. We see that bulges show a more perpendicular trend, while for disk the PDF is consistent with a uniform trend. And if we consider galaxies with both the bulge and the disk component, here for both components we find a higher PDF values for lower value of GOODS-ALMA, so a tendency towards a perpendicular trend for both components, which is consistent with what we found before for the S0 galaxies. And now looking at the separate bulge disk spin filament alignments according to the mass of the bulge. So on the left, we have the alignments for the bulge splitted in bulge mass, and on the right, the disk spin filament alignment splitted according to the bulge mass. We see that for bulges, we tend to have perpendicular alignments both at high and low values for the bulge mass, and this is consistent with mergers being the main channel of formation of the bulges at low redshift. Instead, if we look at the disk, we see a tendency towards perpendicular alignments for high value of bulge mass, and a tendency towards parallel alignments for low values of bulge mass. So here it's more, it's towards higher values of cos gamma. And this tells us that there are multiple channels of formations for the disk at low redshift. So we can have a gas accretion scenario for low values of bulge mass, as well as mergers or other instabilities that can cause the flipping of the alignment from parallel to perpendicular. Then studying more in detail the bulge spin filament alignments, we study them as a function of the kinematic proxies of the bulge, which is the V over sigma parameter, so the rotation velocity over the dispersion. And we separate them according to this parameter, and we see that bulges that are more dispersion dominated, so for low values of V over sigma, we see a tendency towards perpendicular alignments. Instead, bulges that have that are rotation dominated, they are only 17, and they have a tendency towards high cos gamma values, so towards more parallel alignments. And if you look at the bulge-Sarsic index distribution, dispersion dominated bulges again have a tendency have a bulge-Sarsic index equal to 4, towards 4, and this is consistent so with a merger scenario for this type of bulges. Instead, the rotation dominated bulges show a peak for really low bulge-Sarsic index, so they are consistent with being pseudo bulges and having a parallel alignment. This is consistent with being formed by secular processes. And then if we do the same analysis for the disk spin filament alignments, this time according to the V over sigma of the disk, so the rotation of the dispersion of the disk, again, we see dispersion dominated disks having a perpendicular alignment and rotation dominated disk having a more parallel alignment. And this is again consistent with the multiple channels of formation. Now, finally, the last results I want to show are the gas spin filament alignments, because with SAMI we also have H alpha velocity maps, not only the stellar velocity maps. So here we can measure the kinematic position angle from these H alpha velocity maps, which give us the gas kinematic PA. And again, we can repeat the same analysis. And we find reliable gas kinematic maps also starting from a stellar mass of 10 to the 8 solar masses. And again, we find consistent results with the stellar spin filament alignments that I showed before. So galaxies with high stellar mass have a tendency of have a higher PDF at a lower value of cos gamma, so a perpendicular trend, while we have a tendency towards a parallel trend for low stellar mass values. So the main takeaways from this talk are that we find that the mass of the bulge, defined as the geometric combination of stellar mass and bulge total, is the primary parameter of correlation of the spin filament alignments. With the flipping of the spin filament, and this means that the flipping of the spin filament alignments from parallel to perpendicular is linked to the growth of the bulge. And from simulation, we know that these links are the mergers. So mergers are able to show a growth of the bulge, leading to the formation and growth of the bulge, as well as causing the flipping of the spin filament alignments. And if we look separate at the stellar mass and bulge to total parameters, we see that they explain the alignments in a jointly independent way. So jointly because jointly because they both alone they cannot explain the filaments, so we need the filament alignments. We need their combination to fully explain the filament alignments. Instead, independently, because they actually give us different information about the alignments. So the stellar mass traces the galaxy position in the cosmic web and the overall accretion independent from the merger for the merger history. Instead, the bulge to total ratio actually traces gas-rich major mergers, which are actually the most effective in building up bulges in changing the galaxy shape and changing the galaxy angular momentum. So we found different formation pathways for A0 galaxies according to stellar mass. We see that if we actually look at the separate bulge disk spin filament alignments, this can offer us more insights about the formation channel of their galaxies. Thank you.
Thanks a lot, Stefania. So if people have questions, please raise your hands and I will. Oh yeah, Giacomo, go ahead.
Yes, thank you very much. Thank you, Melanie, and thank you, Stefania, for the talk. Just to clarify, this is not my field at all, but I was captured my attention the fact because on Friday at the Journal Club at ESO we discussed, there was a nice presentation about galaxies and rotation of gas and rotation of the of stellar component of galaxies. Basically, and there are cases in which they are co-rotating, cases they see that the co-rotation they do not rotate. There are different rotations basically, and this is basically to 90 degrees and even inversely co-rotated. So there is a 180 degrees. So indeed, in your case, you have measure of gas, the kinematic of gas, and the stars, right? In some cases, I was wondering. So it was told, we understood that this is due to a different formation scenario. So I was wondering whether you can include that also in your study, basically how the rotation of the gas also behaves with respect to, I don't know, to
yes,
filaments.
So yeah, in our case, so here we use the H alpha velocity maps. So we don't use H1 or it's just the H alpha velocity map, and we estimate the alignment. And so the parameter that I show here, so we check how the spin filamental, if the spin and filament alignment depends on this delta PA, which is actually the kinematic misalignment between the gas and stellar component. We don't find a strong trend. So most of the galaxies are aligned in gas and stars. However, they show misalignment, especially early type galaxies. And galaxies with more massive galaxies, they can have a misalignment. But in our case, we don't see this as a main parameter causing the spin filament alignments for the galaxies. So
we actually don't somehow see that the merger, for example, the ones that are supposed to be a merger, most likely to be a merger, to be also the ones in which the misalignment is higher, for example. I don't know, something.
Yes, like so the S0 galaxies here, so these galaxies here, we find stronger trend according to stellar mass, but also if we look at the kinematic misalignment between gas and stars, we see that the signal is dominated by the most misaligned galaxies. So there are cases, particular cases, like if we go into S0 classification where the perpendicular trend is stronger for the most misaligned galaxies. Yes, this is a result that we find and also is in the literature as well.
Okay, thanks. Thank you.
I think we have time for one more question. Giacomo, are there any questions from YouTube?
From YouTube, no, there is no question.
Okay, then I'll take this opportunity to ask a question. So at the very end, you mentioned that the results in terms of growth through mergers are consistent with simulations. Are there any simulation-based studies that actually analyze this in the same way as you, and that they measure the spin filament alignments and the bulge size and link the two?
So yes, so most of the works on simulation, they actually measure the V over sigma parameter because the bulge to total is harder to measure in simulations. So the only work that looks at bulge to total is a work in the eco simulation, but the volume is really small. So it's not that it's not that strong statistically as we see it here in the observations.
Okay, thanks. I'll just check if there's a last final question from the Zoom. Silvio, yes.
Thank you for the talk. It was very nice. I was wondering about your filaments. Do you have a typical size range or typical lengths or radii that your filaments are?
So for the filaments, they are selected according to a cut, let's say in signal to noise, but they don't have like a particular cut in density or or in radial or a radial cut. They're just the most robust features that I could extract. And it's the density field has a weight on the galaxy stellar mass, but yeah, they didn't have any particular cut.
So also the lengths are like any lengths that like, it's a broad range of lengths that you get.
Yes.
And also a quick question: did I get right that you mainly find disks in the filaments? I think it was one of the first slides that showed an image.
Sorry, say again?
That I think one of the more graphic slides that showed an image where it seemed like the disks are mainly found in the filaments. Did I get that right?
The disk, I'm not sure.
We might leave this discussion to afterwards because I think we need to go on with the next speaker. That was a good question.
Okay.
So
Okay.
those who are interested, stay online.
Thank you.
Thank you.
So Ivana and Carlos, if you could, turn your videos on.
Yeah, so it's my pleasure to introduce the second speaker of today's colloquium. So Carlos Gomez-Guijarro is a postdoc at the CEA in Saclay. His research focuses on galaxy formation and evolution across the history of the universe. And today he will tell us about the role of compact star formation in galaxy evolution using the GOODS-ALMA survey. So if you're ready, you can share your screen.
Can you see my screen now?
Yeah, we can see it.
Okay, thanks a lot, Ivana, for the presentation. I'm Carlos Gomez-Guijarro. In today's talk, I will talk a little bit about the latest results from this GOODS-ALMA survey that tries to shed some light on the role of compact star formation in galaxy evolution. You can see here listed some of the main contributors to this survey in different aspects. But let me begin here with a little bit of context. We are interested in this essentially to have a broad understanding of a broad picture of massive galaxy evolution. So if we look at in the local universe, we find one type of galaxy that drags our attention, and these are local elliptical galaxies, because these are the most massive, largest systems. They are void of star formation, but they are also the oldest of the galaxies known in the local universe. So their stellar population tell us that should have formed above redshift 3. So if we go back in time, we know that already at redshift 2, 3 billion years after the Big Bang, we find also some galaxies that resemble like the local elliptical galaxies. We call them compact quiescent galaxies. And these are also reasonably old. They are red and dead galaxies. They don't form stars, but as I say, they have a very distinct feature, which is that they're extremely compact with effective radius of only 1 or 2 kiloparsec. So what researchers believe that these galaxies will evolve into local elliptical galaxies through dry minor mergers that are very efficient processes into puffing up the sizes of galaxies without increasing too much the stellar mass. But how were they formed? So if we look at the more, let's say, secularly evolving scenario for galaxy evolution, it could be that at the highest redshift, we have some extended star-forming galaxy with an extended gas configuration. That gas is funneled to the center of the galaxy and effectively shrinks the effective radius of the galaxy, and after quenching leaves behind this very compact stellar remnant. But there are other scenarios that is more violently driven, and this is the scenario of a gas-rich merger that at high redshift is a very efficient process, putting the gas to the center of collision of the merging galaxies. This process therefore forms lots of stars very quickly, and after the quenching of a star formation will also leave behind this very compact stellar remnant. So in the past 5 to 7 years, with thanks to ALMA, we have been able to study the morphologies of dusty star-forming galaxies above redshift 2. And we see that actually the dust continuum emission is much more compact than the stellar emission at race frame ultraviolet light, as you can see in this example at redshift 4.5, or optical in this other example at redshift 2. You can see one is a more merging system, the other one is a more isolated galaxy, but both have these contours here that represent this dust continuum emission as much more compact than the stellar light. So compactness seems to be a characteristic feature of dusty star-forming galaxies, but there are also some other counterexamples in the literature that find galaxies in which all these dust continuum emission could even encompass all the stellar light. So what is the conclusion that we have in the field on this end? So how systematic is this dust continuum compactness? So it might be that because of a lack of homogeneous sample selection, we are biasing our samples towards observing perhaps more these galaxies that feature this compact star formation, and not others that have more extended star formation, because perhaps we lack of continuous area coverage, or we have a limited UV coverage with the interferometer due to the intrinsic surface brightness profile of the galaxy, that we might be missing some of the emission from the outskirts. So this is what in this ALMA survey that we call GOODS-ALMA tackles. So this is the GOODS-ALMA survey is a 1.1 millimeter blind ALMA survey in the GOODS South field, covering an area of 70 arc-minute square, and it uses two array configuration. One provides the high resolution angular scales, and the other one, more or less at the same depth, provides the low resolution angular scales. So the version 1 of this survey was published in papers that I list here, and it uses this high resolution mosaic. But today I'm going to present the latest results from this version 2 of this survey, which includes this new mosaic at the low resolution and combines it with the high resolution mosaic. So we find more than a factor of 2 more galaxies in doing this exercise. We find 88 sources. These are located in a broad redshift range between 1 and 4. They are fairly massive systems, above 10 to the 10 solar masses, and located around the knee of the number counts at 1.1 millimeters. Among them, we find some interesting cases of so-called optically dark sources. So these are galaxies that they don't have a counterpart in the H band or bluer wavelengths, but they are bright at longer near infrared bands, and of course in the ALMA 1.1 millimeter. and they are believed to be the main contributors for the cosmic star formation rate density above redshift 3 for the most massive galaxies above 10 to the 10. So these are very trendy topic right now, and we have found more examples of these very interesting galaxies. But today I'm going to talk about these sizes and the role in the overall picture of massive galaxy evolution. So what we found now with this new survey is that even the galaxies that were only used in the high angular scales, they are also very, very compact. So our median size is also below one kiloparsec. Of course, I need to talk about what is the range of applicability of these results. We have simulated sources to see what's our completeness limit. You can see here in the bottom right panel, we are roughly 100% complete, about 1 millijansky, for sources that are as big as 1 arc second in full width half max. And then, as I said before, we cover a fairly broad redshift range, and also a fairly broad range in stellar masses. So is there something that we can learn about the size dependency with these two? We don't have much galaxies to do very narrow mass beams, or very narrow redshift beams, but we can see whether at least we see some resemblance on potential trends with the known trends for late type galaxies in optical wavelengths, or for early type galaxies in optical wavelengths. So what we see, if we divide our sample in a high stellar mass beam, low stellar mass beam, high redshift beam, and low redshift beam, we stack them together in the UV plane, and we check whether there is such trends. We see that that's continuum sizes with a stellar mass, and redshift resemble the trends of late type galaxies in the optical, but with a lower normalization that it's more resembling the sizes of early type galaxies. And now if we use this to go back to our previous result of the overall distribution of sizes at 1.1 millimeter, we can plot this bottom right panel. In the x-axis is as a function of flux, what are the sizes as a function of flux, but in this case, in the y-axis, we put all the galaxy to a common redshift and stellar mass, applying the fact that they resemble the trends of late type galaxies. And when we do this above 1 millijansky, which is where we are 100% complete, that's the ungraded area that you see here, we see that is very rare to see galaxies that exhibit a DAS continuum emission as extended as the optical disk. So this is our main result of this first part, that compact DAS continuum emission prevails, and is at above this flux limit, where we are most solidly sure that it's quite rare to find something as extended as an stellar disk in DAS continuum. But now let me try to put this together into the context set by the scaling relations in galaxy evolution. So the first one that you can see here in the top left panel is the so-called main sequence. This main sequence is plotted here as this blue line in the star formation rate stellar mass plot. And our sample is more or less located 50% within the scatter of this scaling relation, and 50% above 3 times the main sequence. And in the top left panel, when one plots this type of relation, you have to make a choice. If you span a broad redshift range, like is this case, either you plot one of these blue lines, one of these main sequence per galaxy, then the plot will be a bit messy, or you scale the star formation rate in such a way that the distance for a given galaxy to the blue line is preserved. So this is what is done here in the top left panel. So an alternative representation is what you see in the bottom right panel, which is just to simply plot what is the distance to that main sequence, to that blue line, as a function of a stellar mass. In this way, we have accounted already naturally for the different main sequence across redshift. You might be familiar already with this type of representation, but it's going to be important for my next slides, because we do the same with other scaling relations. So here you can see what happens, for example, for the depletion timescale. Depletion timescale is defined as the M gas over star formation rate. Is also the inverse of the star forming efficiency. So here in the x-axis, you can see the distance in the main sequence, as in the previous slide. But in the y-axis now is the depletion timescale, with the blue line in this case reflecting the scaling relation for depletion timescale, in this case from Tacconi 2018. The shaded areas reflect the scatter, as in the previous case, and in this case, each point is also scaled for each galaxy, stellar mass, and redshift, because this scaling relation depends on stellar mass and redshift. So then, as in the previous case, why don't we just plot what is the depletion timescale over the depletion timescale of the scaling relation at that stellar mass and redshift, as a function of the distance to the main sequence. So that's what you see here in this other alternative version of the plot. And then what we see is that there is a puzzling subset of the galaxies that exhibit very low, very short depletion timescales that are comparable to those of the galaxies well above the main sequence, but they have moderate star formation rates. They are located within the scatter of the main sequence. So that's we dub them as starbars in the main sequence, starbars because of the very short depletion timescale, but instead they have very moderate star formation rate, unlike the classical starbars well above the main sequence. If we look at this same representation, but instead of depletion timescale in terms of the gas fraction, we see that these galaxies that are now tagged in red, they have very low gas fractions, and they have very high dust temperatures, anomalously low gas fraction and anomalously high dust temperatures compared to the scaling relations at fixed stellar mass and redshift. So also, we thought, okay, maybe it's because we are somehow biased to observing these galaxies, but since it's a survey selected at 1.1 millimeter, it's the best limit. It's M gas, so it's somehow a M gas limited survey. So we are biased against finding galaxies that have a low gas fraction, such as these galaxies. Here you can see in the bottom right panel, as a function of a stellar mass in this shaded gray area, that's our selection function for the completeness limit that I was mentioning before. This is 1 millijansky for galaxy sizes as big as 1 arcsecond. And we see that this subset of galaxies of these starbursts in the main sequence are also very massive. They account for more than half of all our galaxies above 10 to 11. So far, this is in terms of what happens with integrated properties, but at the beginning of the talk, I was talking about sizes. So now let's try to understand what is the role of this very compact star formation in this overall scheme of global properties. So normally in the literature, we usually plot these quantities that I was explaining before: depletion timescale, gas fraction, dust temperatures, as a function of the star formation rate, surface density, sigma SFR. But somehow it's not surprising that depletion timescale correlates with sigma SFR, because star formation rate is in both axes. So that's not surprising. In the middle panel, you can see pretty much of a scatter plot, so perhaps not much to learn. So why don't we try to do this exercise that we have done before of putting together to the same stellar mass and redshift, a fixed stellar mass and redshift, to account for this very different broad and in redshift and in stellar mass, that in the y-axis, and in the x-axis, we only use sizes. So that's what we do here in this bottom row. In the y-axis, you can see what we have been doing in the previous slides: the delta in depletion timescale, gas fraction, and dust temperatures, and the x-axis is a proxy for compactness. So the higher the values in the x-axis, the most compact the star formation is. And when you do this, you see that correlations unveil for the three quantities, and these star bars in the main sequence, they are at the extremes of this trend. So they exhibit the most compact star formation with the shortest depletion timescale, the lowest gas fraction, the highest dust temperatures for galaxies at the same stellar mass and redshift. We thought maybe it's because, again, we are losing some degree of emission in the outskirts. So let's stack them together in the UV plane. That's what is shown here in this red square, and the rest of the sample in the black square. And we see the same result. So observationally, what we find is I try to summarize it here in this sketch. The less amount of gas in a galaxy, the more compact the star forming region becomes, at least for very massive galaxies. So it's as if a star formation rate appears to be sustained by this gas and star formation compression. So even when galaxies have very low gas content, somehow the morphology follows the gas and is able to keep moderate star formation rate. So this is so far what we see in terms of observation empirically. So now let's try to discuss this in the global context of what literature studies have been saying in terms of scenarios for massive galaxy evolution. So if you recall from the first slide, I was talking about this secularly evolving scenario 1. It's nicely summarized in this paper by Takela et al. 2016. And what this paper says is that an externally triggered gas inflow event triggers this compaction phase that is characterized by, of course, very compact star forming region with very short depletion timescale and high gas fraction. Then is the central gas depletion that leads to inside-out quenching. So that phase, what we expect is that in the main sequence, the higher gas content should be related with the most compact star forming region. But what we actually observe is the opposite. In the main sequence, we find that the lowest gas content is associated to the most compact star forming region. So if we go to this other scenario that was showing in the first slide of the merger-driven scenario, in this case, galaxy merger gets the galaxy well above the main sequence. So well above the main sequence, the galaxy is characterized by compact star formation and a high gas content. And it's when the galaxy goes down to quiescent that passes through incidentally through the main sequence, and at that point, it's natural that it will have a low gas content. So in a way, our observables fit fine with this possibility, but there is also a subtlety, is that at fixed stellar mass and redshift, what we find is that even at the main sequence, the star forming region are even more compact than well above the main sequence. So this fact and the fact that now this puzzling subset of galaxies doesn't seem to be is no longer a rare case, but we see that more than half of our galaxies above 10 to the 11 are of this type. We were a bit puzzled and trying to interpret this. So do we have enough mergers actually at this high end to account for all these galaxies or not? So perhaps there is a higher layer of things that are happening, and it's not all the times needed that you have this very gas-rich major merger funneling the gas to the center. And at least what theory says is that you can put the gas together either externally or internally driven. So externally driven, of course, through mergers, major, minor mergers, but also through clamp migration if the galaxy has enough gas in the disk. But what will be even more important is that as the galaxy is doing this, when the gas reservoir is consumed and doesn't accrete more gas, it becomes more compact, holding the star formation rate. So in this case, in this scenario, in comparison to the previous one, the galaxies will be kept in the main sequence longer, even when the gas fractions are low and they are presumably on their way to quiescent. It might explain why we see that many in the high mass end. So therefore, not requiring all of them to go through this violent merger phase. So I leave you here with the conclusion slide, and the takeaway point is essentially that even with a very good coverage in the different angular scales, we find that compact dust emission, compact star-forming regions in dusty star-forming galaxies prevail. It's quite rare to find that above 1 millijansky, the dust continuum region reaches the size of the stellar disk. We find this passing subset of galaxies that exhibit starburst-like depletion timescale, but at the same time they have low gas fraction, very high dust temperatures. They are very anomalous in this way. We find correlations between a geometrical property like the size of the ongoing star-forming region and these properties of depletion timescale, gas fraction, and dust temperature when we account for the stellar mass and redshift difference. And these starbursts in the main sequence, they are the extreme cases of these trends. So altogether, it seems to tell us that the star formation rate is somehow sustaining very massive star forming galaxies, and it keeps them within the main sequence, and perhaps is this gas and star formation compression that allows to hold their star formation rate. So thank you very much for your attention. If you have questions.
Thank you for your talk. If you're on Zoom and you have a question, you can raise your hand. And if you're on YouTube, you can just drop a question in the chat. So I see one question, Paola.
Yeah, hello, Carlos. Nice to meet you. The question I have is related to the ALMA data, because I'm not sure that while stacking, you may see faint extended emission that you miss anyway if you don't have a shorter configuration or even ACA compact array information. So I was wondering whether you have estimated how much you may miss. And then, of course, this compact issue may disappear.
Yeah, so that's a very important point. So two things. So one is because of the intrinsic size of star-forming galaxies at these redshifts that are the effective radius. So by pure interferometry arguments, we don't expect to lose angular scales with these two configurations because the maximum recoverable scale will be 4 arcseconds. So in this case, with the two configurations, we don't expect to lose much from mathematical reasons. Then the other thing is whether the intrinsic surface brightness profile of the galaxy has a shape in which we don't reach the limit at a given scale. So if the gas and dust is more centrally concentrated, maybe we are biased to this part and we are losing the outskirts because of signal to noise issues. So this is why we were stacking everything and to go to higher signal to noise to mitigate for this. In this case, we see the same result. And then yes, we have actually recently quantified what would be the scale at which we are losing a significant fraction of the gas. So, for example, if the galaxy is, if I recall the number, larger, if the gas configuration was molecular gas was larger than 1 arcsecond in full width at max, then there we will be losing a factor of 2. So at least in the regime where we are complete, which is below this 1 arcsecond, we are certain that this is not happening. If there is a regime, maybe perhaps a lower mass regime in which this is actually the case, and you have a more extended gas configuration, then there, yes, then there we will be losing some flow.
Okay, thanks.
Thank you, Paola. Is there any other question? I don't see any question on the YouTube chat or on Zoom. So I guess we can close. Should I give it back to you, Giacomo?
Yes, thank you very much. Thank you, Carlos, and thank you, Stefania, for the talk. Thank you, Ivana and Melanie, for chairing the sessions, and thank you for the participants. As I said, the video will stay on YouTube, so please keep you can watch them and watch all the other previous events. And with this, I will invite you to come to the next series, which is going to happen next week. But still, as I said, please go to our pages and you can still see and watch access the CVs of our speakers. Thank you very much, Carlos and Stefania, once again, and good luck for your career. And see you soon.
Thank you.
Bye-bye.
Thank you. Bye.
Bye. Thanks.
Bye.